Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a neural network model using R. Even before I demonstrate how to build a neural network model using R, may I request you to subscribe to my channel, also like and share my videos. There are three important points to remember when we build a neural network model. Firstly, this approach is a non-parametric approach towards model building. What do I mean by non-parametric approach? It simply means that there are no distributional assumptions about the data. When we build a neural network model, we don't say that the dependent variable should follow a certain distribution, the independent variable should be uncorrelated, the error term should follow a particular distribution. We don't make any of these assumptions. I repeat, we don't make any assumption about the data. And hence, we can go ahead and call this as a non-parametric approach towards model building. The second point here is that when you have a dependent variable which has a linear relationship with the independent variable, you can go ahead and use the linear regression model. But the question is, what when there is a non-linear relationship between the dependent and the independent variable? If there is a non-linear relationship between the dependent and the independent variable, by definition, it becomes very difficult to model its behavior using a linear regression model. So what do? This is where a neural network model comes to our rescue, because a neural network model can handle non-linearity much better than some of the other statistical models. Hence, neural network model is widely regarded as a gold standard when it comes to modeling non-linear data. The third important point is neural network model works like a black box approach. With this approach, you will be able to generate your predictions, you will be able to get the confusion metrics, but the output is less interpretable. Imagine when you build a linear regression model, at the end of the model building activity, you have a fitted regression line. You have R square, you have adjusted R square, you have the ANOVA table, you have the coefficients table. You also can generate a lot of plots and such things. In comparison to a linear regression model and the output of a linear regression model, the output of a neural network model is very poor. You do not get such rich results, and therefore we say that it works more like a black box approach. It becomes very difficult to interpret which node is talking to which other node. How is one node related to another node in a neural network model? So these are the 3 points. Neural network is good for nonlinear data. It's a non-parametric approach. Thirdly, it's a black box approach, and therefore it is less interpretable. With this, I will proceed to introduce you to the data that we will be working on. As you can see here, the source data is in Excel. I have got 4 variables. The very first variable is the dependent variable. This is a typical banking problem. Very many times people take the loan, and after taking the loan, they default upon the payment of a loan. So the dependent variable here is whether a customer defaults on the payment of a loan. We have looked at historical data. If a person is a non-defaulter, we are calling it as 0. If a person has defaulted on the payment of a loan, we are calling it as 1. So 1 refers to defaulters and 0 refers to non-defaulters. The first variable is the dependent variable. The rest of the variables will act as independent variables. So I've kept it very simple in this particular case. I'm using 3 variables: income, debt income ratio, and years spent with the current employer as the independent variables. So using a customer's income, debt income ratio, and years that he has spent with the current employer, we want to classify whether a person will be a defaulter or a non-defaulter. Let me move on to R now. With this background about the data, the next thing that we are going to do is to do some coding in R so that we can build a basic neural network model. The first step here would be to import the data set. Let me go ahead and import the data set very quickly. There is a very simple function in R Studio which is called as read.csv. You can see here, this is import data. I'm going to use read.csv to pull the data set into R Studio. Once you bring the data set into R Studio, the next thing that you can do is to view the data. You can use the view command to go ahead and view the data set. As you can see here, R gives me the preview of the data set. The first variable is default. This is the same data set that we were looking at in spreadsheet. Then these are the three independent variables: income, debt to income ratio, and years for the current employer. The sample size here is 400, and we have got 4 columns. Let me close this particular file. What is the next thing that I wish to do? The next thing that I wish to do is simply study the structure of the data set. How do I study the structure of the data set? You can simply use the str command, which will generate the structure of the data set. You can see here in the console window, what R does is it gives you the structure of the data set. There are 400 observations with 4 variables, and you can see here some of the values. We need to be slightly sensitive to the independent variables. You can see here, when it comes to income, we have triple digit numbers. We have numbers like 380, 660, 800, so on and so forth. When it comes to debt to income ratio, since it's a ratio variable, you have it in the form of 3.6, mostly single digit numbers. Years spent with the current employer, they are in single digit numbers as well. This is a problem when we model the data. Why is it a problem? You can see here, when it comes to the variable income, it has triple digit numbers. When it comes to some of the other variables, it has single digit numbers. So income has large values. So when we build a model, larger values tend to dominate the smaller values. To avoid this problem, what we do is we usually tend to standardize the data. Sometimes we can normalize the data as well before building any model, right? So as a simple thumb rule, when we have different variables measured in different units, and some of these variables tend to be extremely large and others are extremely small, to avoid the domination of those variables with large values on those variables with smaller values, we can use normalization as a technique. So this is part of data pre-processing. So you can see here, I'm going to do data pre-processing at this stage. We can begin by normalizing the data. How do we normalize the data? We can use what is called as max-min normalization. There's a very simple formula to normalize any data. What is this formula that we will be using? The formula that we will be using is to take the variable, let's say debt to income ratio. This is the way I'm going to normalize the data. You can see here, I'm going to subtract the minimum value of my independent variable from every value divided by the range. You can see here in the denominator, I'm using maximum value minus minimum value of that particular column. Maximum minus minimum will give you the range that will be used in the denominator, and in the numerator, from each and every value, I'm subtracting the minimum. So very simple. How do we normalize the data? Take the column, subtract the minimum value divided by the range. So this will ensure that I have normalized my data. I'm going to repeat the same procedure of normalization for the other 2 variables as well. I'll be normalizing the variable income now. The formula is the same. You can see here, subtract the minimum, divide by the range. The last of the variable that I have for normalization is years spent with the current employer. This is the third independent variable that I have. I'm using the same formula to normalize. So at this stage, what I have is the normalized data. What you want to do at this stage is to simply view the data. You can see here, now all the values after normalization have been reduced. You can see here, each and every value will lie between 0 and 1. So the first person income after normalization has come down to 0.27. The second person's income is 0.75. The same holds good for debt to income as well as the third variable. Each and every value in these three columns will lie between 0 and 1. This is the effect of normalization. Earlier, you had extremely large values. So this takes care of the scaling process. So at this stage, what we have done is to simply pre-process the data. What is the next step? The next step is to partition the data. Why do we have to partition the data? Simply because when we build any model, we will create two sets. The first set is called as the training data, and as the name itself suggests, the training data will be used to train the model. The second set of the data is called as test data, which will be used to test the performance of the model. Let us go ahead and set the seed here. You can use any number. This will ensure repeatability. After setting the seed, the next thing that I'm going to do here is to create two different samples. How do I create this? You can see here, I have specified a variable which is called as int. I'm going to use the sample command and I'm going to say 2. 70% under the probability argument, 70%, I'm giving this as 0.7, which means that 70% will be assigned the value of 1, which I will be using for training. The balance 30% will be used for testing the data set. I'll go ahead and execute this particular code. Now you can just see what is there in int. You can see here, it has created 400 values wherein you have numbers like 2 and 1. The value 1 can be used to assign the samples to the training data set, while the value 2 will be used to assign the records to test data set. What is the next step here? The next step is to create the training data set. We would like to create the training data set. So there's a very simple command to create the training data set. You can see here, data. Here I will be using ind equals 1. Wherever it is 1, I will be assigning it as training. And similarly, I can just copy paste this particular code. I will be calling this as testing data set. Here, I will just be changing the logic to 2. So right now, I've got two different data sets. One is called as training, and the second one is called as test data set. You can see here, out of 400 observation, the sample size for training data set is 281. Roughly 70% of the cases have gone into training data set, and the balance 119 observations have gone into testing data set. We are all set to build our neural network model. So far, what we have done is what is called as pre-processing. Now, we will go ahead and import certain packages so that we can go ahead and build a neural network model. In line number 23, you can see here, I'll be building a neural network model. It's important to install the packages. There is a spelling mistake here. Install.packages of neural net. This is the command that you need to give to install the package. Now, since I've already installed, I'll not use this once again. I will ignore this particular command. I can go ahead and simply call the library. and you have to set the seed once again. As I said, this is for repeatability purpose. There's a very simple function that you can use to go ahead and build the neural network model. What is that function? I'm just going to very quickly show you what is the function that we will be using. So in line number 28, we can see the function that we will be using. You can see here, the function name is neural net. Very easy to remember. The package name is neural net. The function name is also neural net. You can open parenthesis. You can specify the name of the dependent variable. In this case, the name of the dependent variable is default. Then you can use a tilde symbol to separate the dependent variable and the independent variable. The first variable that I will be using here is debt income ratio. Plus, you can specify the second input variable, which is income, and the third input variable, which is years spent with the current employer. The data that will be used to build the neural network model is training data. I will not be using the testing data set as of now. Curiously, this is a very, very important step. You can see here, hidden equals 1. Since this is a very basic model, I'm building a neural network model for the very first time. I'm going to specify hidden equals 1. Hidden equals 1 does not mean that we have only one hidden layer. Of course, we have one hidden layer, but here hidden equals 1 means that we have one neuron in that hidden layer. If you specify a value of 3, it means that the hidden layer will have 3 neurons. The error function is equal to CE, which means cross entropy error function will be used. As an alternative, you can also use SSE or sum of squared errors. You can use this in the hyperparameter tuning stage. But as of now, I want to keep it very, very simple. And therefore, error function that I have specified is cross entropy. Finally, linear.output can be specified as false. I can save this output. So I'm going to save this in an object which is called as n. Let me go ahead and specify this as n. If you want to dig out more and more details about neural network, I would request you to use this particular command, help of neural net. This will explain in detail what are the arguments that you can use in R for different parameters here. But I want to keep it very simple, so I'm just going to ignore the help command. I've gone and executed a neural network model. After building this neural network model, let me see in the console window, I'm not getting any error, which means that this particular model has run successfully. The next thing that I wish to show you is to show you the architecture of the neural network model. How do you display the architecture? Simply use the plot command, and our model is stored in the object n, plot of n. This is what you need to give. Let me go ahead and execute plot of n. You can see here, this is how the neural network architecture looks like. A lot of things are happening in this model. You can see here, there are a few arrows. Let us interpret this from left to right. You can see here, there are 3 arrows. One, this is the first arrow, this is the second arrow, and this is the third arrow. Debt to income ratio, income, and years with the current employer. These are the 3 input variables which I am pushing into the input layer. These 3 circles that you see here represent the input layer. I repeat, these 3 circles, they're also called as neurons or nodes. These 3 circles basically constitute the input layer. At the other end, you have one single circle, which is called as the output layer. So the first 3 circles are the input layer. The final circle that you see at the other extreme is the output layer. And the circle or the node, which is right at the center between the input layer and the output layer, is the hidden layer. So in a typical neural network, you have 3 layers. The first set of layers, the first layer is called as the input layer. The second layer is called as hidden layer, and the third layer is called as the output layer. This is what we call as MLP, or multi-layer perceptron. I repeat, multi-layer perceptron. In a multi-layer perceptron, we have three layers: input layer, hidden layer, and output layer. Please observe that here the input layer is connected to every other neuron before this particular layer. It is also connected to every layer, to every neuron in the next layer. So we give it a fancy name. We call this as a fully connected network. I repeat, this kind of a model is called as a fully connected network. Why do we call this as a fully connected network? A node which is connected with every other node in the previous layer. Also, this node is connected to every neuron in the next layer. Therefore, it is called as fully connected network. By the way, within the node, if you observe the input layer, within this node, these two neurons are not connected, they are unconnected. So this neuron is not talking to this particular neuron. Similarly, this particular neuron here is not talking to this neuron. So within the nodes, they may not, within the layer, they may not be talking to each other. Let me explain what is happening in this particular neural network. The input variables, or the independent variables, are pushed into the input layer. The neural network does some kind of processing here, and it assigns what is called as weights, which means that the weights have to be learned from the data. These numbers that you see, 1.1, 1.31, or 0.77, minus 0.84, the numbers that you see on top of the arrow represent the weights of the neural network model. This is very, very important for us to understand. The numbers that you see on top of the arrow represent the weights. The weights have to be learned by the neural network model from the data. If the neural network model learns the wrong weights, you will be getting wrong predictions. On the other hand, if the neural network model assigns the right weights to each input variable, you will get the right predictions at the end of the day. You can see here there's a blue line, and neural network model says that the value is 0.08163. Now this 0.08163 represents the constant. It is more or less like the constant that is generated in a typical linear regression model. Further, you have one more arrow here. This is again the weight, and this is like the constant that we get. So how does the prediction happen? Very simply, you have to take the weight, multiply it by debt to income ratio, add it with the sum product of the weight 0.77 multiplied by the income of the first person, plus take the weight, multiply it with the years with the current employer of the third variable. Once you take the sum product, you can go ahead and add the constant value that will be passed in a function which is called as the activation function. By default, a sigmoid activation function is used. Once we get the output of node 4, what happens at the next stage is we have to take this value, multiply the weight with the output of node number 4 to generate the output value. At an overall level, you can see here the error is 160.87. So neural network has run 14,055 steps or iterations, and then it has converged on the solution. So the neural network model tries to reduce the error in each stage. It has run 14,055 steps, and finally we have obtained an error value of 160.87. Can we improve upon this error? A high value of error means we have a less accurate model. A low value of error means that we have a more accurate model. Now, let's go back to the R code. So this is the R code. Let's type in some more code to see the predictions. At this stage, what I want to do is generate the predictions for the model. I want to generate the predictions for the model. So I'm going to write more code here at this stage. In line number 36, you can see here, we'll be generating the predictions for the neural network model. We can use what is called as the compute function. The compute function helps me generate the predictions. You can see here, compute of n. Remember, n is where I have run the neural network model and saved the object. I'll be running this on the training data set minus the first column. I don't want the first column because the first column has the dependent variable. I'll be generating the predictions and saving the output in an object which is called as output. What next? After running the output, you can look at the top 5 cases here. You can see here in the console window, you can see here the first person has a predicted value of 0.37. What does this mean? This simply means that when it comes to the first person, there's a 37% chance that he is going to be a defaulter. Very important. There's a 37% chance of him being a defaulter, which automatically means that there is a 63% chance of him being a non-defaulter. You have to compare 0.37 with 0.63. How do I get 0.63? Simply 1 minus 0.37 will be giving me 0.63. So since 0.63 is greater than 0.37, so there's a 60% chance that a person will be a non-defaulter, and therefore we can go ahead and call the first person here as a non-defaulter. Compare this with the second value, 0.66, which is clearly greater than 50%. So which means that there is a 66% chance that the second person will be a defaulter. 66% is pretty high, so you can go ahead and call the second person as a defaulter. When you look at the rest of the cases are all less than 0.5, meaning that the rest of the cases will be non-defaulters. So this is just giving you a preview of only 5 cases. Remember, in the training data set, we have 281 cases. So we have generated the predictions and we have displayed the first 5 cases. What next? The next would be to simply look at the first record. Look at the first record here. The first person in the training data set, he is being called as a defaulter, but the value of 1 means that he is a defaulter. When you compare it with our neural network prediction, my apologies, you can see here the first person is a defaulter because this is the actual value. Compare it with the neural network predicted value. The predicted probability is 0.37. So the neural network model will be calling him as a non-defaulter, which is clearly a misclassification. So our neural network model has got the very first record wrong. The rest of the things are nothing but the values of the independent variable, which will be used to generate the prediction. I've taken this just as a test case to tell you how the neural network model works. Now, let's look at the mathematical calculation at the back end. We can look at what is the internal calculation behind a neural network algorithm. You can see here. I'm going to show you a code which is used at the backend. Line number 42, you have the first value. This is like the constant term which I was mentioning. You can see here 0.75 is the income value for the first person, which is what I am using here. 0.78 is nothing but the weight for income. Similarly, you can look at 0.82. This is nothing but the value for debt income ratio. We're going to multiply it with the weight for debt income ratio. The same argument holds good even for years with the current employer. It is 0.6666, so on and so forth. I'm using this particular years with the current employer value multiplying with the weight here. So when you take the sum product of each and every variable with its respective weights, add it with the constant term, you will get the input value for node 4. So this is what we are calling as IN4. Once you get the input value, what is the next step? The next step is to pass it through a function which is called as sigmoid function. Let us quickly look at what is the value of IN4. It is 1.18. We're going to take this value and pass it through the sigmoid activation function. You can see here 1 divided by 1 plus exponential of minus IN4. So here we are using the value of 1.18. Let me see what is the output value here. We are going to get an output value of 0.76. So right now, what we have is nothing but 0.76. This is not the end of the story. We have to do one more level of calculation, which is to take this value and pass it through the activation function. So I'm going to take this output 4, multiply it by its respective weight of 8.78, add the constant and store it as input for fifth node. Finally, you can see here what is the value of input 5, IN5. You're getting a value of minus 0.46. In the last step, what we are going to do is we are going to take this input value and pass it through an activation function. You can see here, IN5, I've used this under the activation function. Let me check out the value of output at node 5. You can see here 0.38 or 38% probability. Let's go ahead and revisit the score for the first individual. You can see here the score is 0.37. Now the small change here, I'm getting 37%, which is the neural network predicted value, and I've shown you how does neural network arrive at this particular value. When I manually did it, I'm getting 38%. There could be small rounding off error that can be ignored, but this is how neural network computes the predicted probability of default for every individual. Let me just go ahead and revisit the steps here. So I'm just taking the input variables, multiplying it by its respective weights, adding the constant value to get input 4. This I'm passing through an activation function. This is the formula for a sigmoid activation function, and I'll be saving this as output 4. This output 4, I'm going to again multiply it by its respective weight, add a constant value, create an object called as input 5, which will be passed through an activation function to finally give you the output value at output node. So the output node value here that I'm getting is 38%, which simply means that you can see here 38%. This simply means that there's a 38% chance that the person will default upon taking the loan. Let's now go on to do the next step. What is the next step? The next step is to check the accuracy on the training data. So in line number 51, I will be checking whether this model is accurate or not. How do we check for the accuracy of the model? Let's first check the accuracy on the training data set. We can go ahead and do the same thing in the test data set as well. You can see here, I'm using the compute function. I'm calling the object n where I have saved the output of the neural network model. I'm dropping the very first variable from the training data set, and I will save this as an object output. After creating this particular object, the next stage would be to generate predictions. You can see here, output has a object which is called as net.result. This I'm going to save as P1. P1 is nothing but predictions. You can see here for 281 records, we have generated the predictions. These are the predicted probability. You can see here in the console window. Let me scroll up. These are the predicted probabilities. We are going to use a simple thumb rule, that is, if the predicted probability is greater than 0.5, we will call him as a defaulter. If the predicted value is less than 0.5, we will be calling him as a non-defaulter. Further, as I told you, we're going to use a simple if-else logic. If the P1 value is greater than 0.5, I will call him as defaulter, else as a non-defaulter. So I have got my predicted class at this stage. What's the next step? Once you do this, very simple and easy, now you can generate the confusion matrix. These are the confusion matrix values. You can see here, you can use a table function to generate the confusion matrix. Here, I'm going to call the object and your confusion matrix is ready. How do we interpret the confusion matrix here? Along the column, what you have is the predicted value, predicted by neural network as 0 or 1. And along the row, you have the actual class. The diagonal elements always represent the correct classification. You can see here, row says 0, column says 0, which means 172 non-defaulters have been correctly classified as non-defaulters. So this represents the correct classification. Similarly, when you look at the number 23, this again represents the correct classification. Why? Because the predicted class is 1, the actual class is also 1. So 23 defaulters have been correctly classified as defaulters. 172 non-defaulters have been correctly classified as non-defaulters. The number 69 represents misclassification. Similarly, the number 17 represents misclassification. So if you want to check the accuracy of the model, you can use a simple logic. What is that simple logic? You can just take the sum of the diagonal elements. You can see here, we can evaluate the accuracy of the model in the training data. I'm going to say sum of diagonal elements of tab 1 divided by sum of each and every element. Here you can see here the accuracy of the model in the training data set is 69%, right? It is 69.39. You can just round it off and say approximately 70% is the accuracy of the model, which is not bad. You've just used one neuron in the hidden layer. And with one neuron in the hidden layer, we are able to get 70% accuracy. Now, the next stage would be to do the same thing and replicate what we have done so far, which means we will be generating the confusion matrix, but this time on the test data. So you can see here, as I scroll up, this bit of code from line number 52, I can just copy paste, except that I have to just change the argument here from training to test. The rest of the things will remain the same. So since I've already done this for training data set, I will not be explaining the same thing again. I'll just copy paste the codes above and you can just generate the accuracy for the test model. You can see here in line number 65, we are computing the predicted probabilities. We are creating P2. We are using the same logic greater than 0.5. We are going to call it as 1, else 0. We can generate the confusion matrix. So this is the confusion matrix on the test data. Along the column, we have predicted values, and along the rows, we have the actual value. 0 along the row and this 0 along the column. If you see this number 77, it means that 77 non-defaulters have been correctly classified as non-defaulters by the neural network model. Similarly, 8 defaulters have been correctly classified as defaulters. So what is the overall accuracy of the model? You can see here the overall accuracy of the model on the test data is 71%. I repeat, the overall accuracy of the model on the test data is 71%, which means that when you compare the accuracy for the training, which was 69%, and on the test, I'm getting 71%, which is very, very close to each other. Since it is very, very close to each other, you can say that this is a good model. This is a stable model. I repeat, this is a stable model. There is no overfitting of the data. Can we improve the accuracy of the model? Yes, of course, we can try to improve the accuracy of the model. So in this video, my goal was to build a simple vanilla neural network model. As you can see here, I've just used one neuron, right? You can see here, let me scroll up. You can see here in line number 28, I've just used one neuron only. With one neuron, we are able to get approximately 69% accuracy, approximately 70% accuracy in the training data set, and 71% accuracy in the test data set. How can we improve upon this model? That I will be talking about in the later videos. So with this, I have come to the end of today's video. In today's video, we have looked at how to build a neural network model to predict the behavior of defaulters. To summarize, we have said that neural network model is very useful to build non-linear relationships. When you have non-linear relationships in the data, neural network can be used to handle non-linear relationships. Second one is that it is a non-parametric approach towards model building. It works like a black box. We have taken the data, we have split the data as training and testing. We check the accuracy of training as well as test. And we have come to the conclusion that this model is more or less stable model, which means there is no overfitting in this particular model. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much. Have a great day ahead.